Good morning, everyone. Miss Butler here. I have a video on how to balance redox reactions. And so remember from our last video, in a redox reaction, we are moving electrons from one atom to the other. So if you look, I have substance A or element A. It is moving its electron to element B. So A, in this case, we say is oxidized because it's losing the electron, and B is being reduced because it's gaining that electron. These reactions can be tricky to balance because you have to keep track of not only that the elements are balanced on either side, but also that the charge is conserved, meaning that the number of electrons given is the same as the number of electrons taken. And so we're going to start off with some easy ones that you could probably just look at and balance like we did in regular chem, but we're going to start to then amp up the difficulty to help you balance these redox reactions. All right, our first step in balancing a redox reaction is to assign oxidation numbers and figure out what element is oxidized and what element is reduced. And so a couple of things. What are these oxidation numbers? Well, they're going to be positive or negative numbers, which we learned how to assign them last video, but it helps indicate or tell us the amount of electrons gained or lost or losing an atom's done. So how many electrons has it gained, how many has it lost, things like that. And really we use them to keep track of the charge when we're trying to balance a redox reaction. So here I have an unbalanced equation. It might be already balanced on your sheet. It's not a difficult one to balance. I would give this to regular chem students, but I want to start easy and show you how to balance a redox reaction before we amp up the difficulty. So my first thing is we're going to assign oxidation numbers. So I know carbon is an element by itself and there's no charge on it. That's 0. Elemental oxygen is O2. And then over here, my oxygen is going to be -2, and there's one of those. And so that means my copper has to be a +2. And what you can see is over here is this is electrically neutral. These guys don't have a charge. And then over here, now my copper and my oxygen both have charges associated with them in the form of oxidation numbers. So they must have gained or lost electrons. And so remember the little ways to remember. We have oil rig, oxidation is loss and reduction is gaining, or my personal favorite, Leo, says grr. So that means loss of electrons, oxidation, and gain electrons is reduction. So I just typed those in to make it look a little neater. Let's see what the next step is in balancing the redox reaction. Now that we have the oxidation numbers, let's see what element is oxidized and what is reduced. So copper went from an oxidation number of 0 to a +2, and remember electrons are negative, so because it became positive, that means it lost electrons. It lost those negatively charged electrons. And when we lose electrons, Leo, lose electrons, we are oxidized. So in this case, copper is oxidized. And then we have oxygen, who goes from 0 to -2. Oxygen gained electrons. So gain electrons, gain electrons, reduction. So oxygen is reduced. So our next step after figuring out what is oxidized and reduced is splitting these into what we call the half reactions. So we basically take apart the equation and make it 2 mini equations. So the first one is the oxidation. We said copper was oxidized, and so this is the half reaction for the oxidation of copper. Copper neutral to copper 2+ ion. So this is the reaction for losing electrons. The reduction half reaction was O2 in its standard state going to O with a -2 charge. So this is the half reaction for gaining electrons. Notice originally the Cu2+ and the O2 were bonded together in my reaction. All I did was split them back into the ions, and we will eventually put them back together at the end. But I'm focusing just on what elements were oxidized and what were reduced for these half reactions. So our next step, and this is very, very important, we have to balance the elements. So if I look at my oxidation, I have 1 copper atom and 1 copper atom. Don't worry about the charge yet. I'm just talking about the elements. So I do not need to balance this because there's 1 of each. The reduction half reaction, on the other hand, I have 2 oxygens and only 1 oxygen here. So I'm going to balance those like we would in regular chemistry with big coefficients. So I put a 2 in front of the oxygen ion. So that way I have 2 oxygens on this side and 2 on this side. So balance the elements is your really much right when you split into your half reactions. That's your first step. It's very, very important. Okay, next step is in each half reaction, we need to add electrons to balance the charge. So if you look originally, let me grab my pencil. On this side, I had a 0 and a +2. But charge needs to be conserved in chemical reactions. So what this means is this guy has 0, this has +2, but I need both of these to be the same. They don't have to both be 0, but they need to be the same. How can I do that? I'm going to add 2 electrons to the product side, because now on this side, I have my 0, I have my +2, and this is -2. You can see that those would cancel to get me back to 0. Again, you don't have to be at 0, you just have to have both sides equal each other. So I'm adding 2 electrons. Let's check out what we do on the other half reaction, the reduction half reaction. I have 0 for my oxygen. Let's go over here. And then I have a -2, but there are 2 of them. That's a -4, because really what I have over here is like this, O2, O -2, O -2. So I have a -4 on my product side. So what am I going to do? I'm going to add 4 electrons, because then it'll be 0, -4, and this is a -4. You can see that both sides have -4 for the charges, so they are equal. That's how we add the electrons. One little trick is I always double check for a reduction half reaction, the electrons are in the reactants. Reduction reactants for those electrons. All right, the next thing is before we put these half reactions back together, I need to be guaranteed that the electrons will cancel out. I don't know about you, but I've never seen electrons included in a balanced equation. So we need to have it so that they cancel, because however many electrons the oxidation is giving, the reduction part of the reaction needs to take that exact same amount of electrons. So on this side I have 2, this side I have 4. So I want both of these to be 4. So you're looking for your common factor. So I'm going to multiply this entire half reaction by 2, so that way there'll be 2 coppers, 2 copper ions, and 4 electrons. So when I am ready to put them back together, there will be 4 electrons on this side and 4 electrons on the product side. Starting to get smaller as this problem gets longer. All I did here was take this 2 and multiply it through the entire reaction, or the entire half reaction. All right. Now this one's not so bad, but sometimes these guys get kind of long, so you have to be extra careful. What I'm going to do is I'm going to put together the reactants of the reduction, that's here in blue, the reactant of the oxidation, that's here, and then I'm going to do my arrow, and I'm going to take the products of the oxidation and the products of the reduction. It doesn't matter the order you write them, as long as anything that's a reactant on each half reaction becomes a reactant, and anything that's a product becomes a product. So being neat and kind of having a process that you follow every time is helpful, so you don't miss anything. All right, so now I'm getting closer to my final balanced equation. I notice that I have 4 electrons on the reactant side, 4 electrons on the product side, so those are going to nicely cancel each other out. And then all I did was rewrite that equation without the electrons in there, and we are good to go. The other option is I could put these guys back together and say that there are 2 copper oxides, so copper 2 oxide, so 2 CuOs like we had in that original equation, but leaving it like this is acceptable as well. So we have our balanced equation, and I'm running out of room. This problem is squishing me, but I know this one you probably could have balanced by looking at it, but I wanted you to see the process of how we split it into the half reactions. We double check that the electrons are canceling and that it ends up being electrically neutral, and we prove that by getting the electrons to cancel. All right, so here's what we are going to do. You are going to assign your oxidation numbers and figure out what's reduced and what's oxidized, and then divide your equation into oxidation and reduction half reactions. So whatever is being oxidized goes on one side, whatever is being reduced goes in the other. Then the important step, balance the elements. You will skip hydrogen and oxygen. We balance hydrogen and oxygen differently in these redox reactions. Remember, I told you we are starting with an easy one. So I will show you an example where we balance the elements and then save hydrogen and oxygen. But just to kind of preview, here's how we balance. So if the oxygens are not balanced, we will balance the oxygens by adding water. So I know on the last one there were oxygens, but oxygen was the only thing. I'm talking about if I have a chemical that has regular elements and oxygen as part of the half reaction. So we're going to add waters to the appropriate side, and those O's in the H2O will balance the oxygens, and then we'll balance hydrogens by adding H+ ions. Okay, then this is what we saw in the next one because we kind of skipped over this. Balance the charge by adding electrons for each side. Remember, reduction reactants. The electrons should be in the reactant side for the reduction. You'll multiply the half reactions to make the electrons equal. So just find a coefficient. You might have to do both half reactions. You might just have to multiply one. Sometimes they both already have the same number of electrons. And then you will cancel out any common terms. Common terms meaning they're the same on the reactant side and product. It's usually electrons, but sometimes it's going to be water and H pluses. And then you will recombine the two half reactions. Okay, if it is basic, so most of the time you're going to have acidic solution, which is why we can add H plus in waters. But if it is basic, you're going to do everything the same. But we have a small tweak, which means at the end we're going to add hydroxides because there's actually, if there's any H plus floating around in any capacity, those will combine with OH minus to make water. I will show you how to do this before the end of this video. And then you just double check your answers, make sure everything looks balanced. All right, I want you to try this one. It doesn't have any trickiness with the oxygens or hydrogens. So all you're going to do is let's look and assign oxidation numbers, figure out what element is oxidized and reduced, split them into the half reactions, balance the elements, add your electrons, and then recombine and cancel. So I'm going to pause the video. I really do want you to try this. So set a timer for maybe 2.5 to 3 minutes. Try this problem and the answer will come up in 3, 2, 1. All right, hopefully your oxidation numbers match and you figured out that magnesium was oxidized and the mercury was reduced. So my oxidation half reaction, I have neutral magnesium to magnesium 2+. And then my reduction was the Hg2+ right here to the Hg2. So my first step was to put a big 2 in front of this Hg because of the little 2 here. So I balanced this element. My magnesiums were already balanced. And then I did my electrons. I have 0 on this side and I have a +2, so I need 2 electrons over here. On this side, the charge is +2, okay, and there's only this whole ion is +2, whereas over here, I have a +2, but there are 2 of these ions, so a +4, right, because I have 2 Hg2+. So in that case, I need to add 2 electrons to my reactant side. Remember, reduction electrons in the reactants, reduction reactants. And then I combined. So I took my Mg and then my electrons and my 2 Hg2+ right here. And then my products, Mg2+ and 2 electrons and my Hg2 2+. And I canceled out my electrons. I did not need to multiply because I already had 2 electrons on both sides. So once I canceled out those electrons, I was able to get my balanced equation that's balanced based off the elements and the charge. All right, let's balance this one together, and I prefer you just kind of sit back and watch and take it in, and then you can pause the video when we're done and write it all down, but I don't want you to miss anything. So my first step is assign oxidation numbers. I know oxygen is a -2, and there are 4 of them, so really this is a -8, like it's contributing -8, and this ion has a -1 charge. So that means my 1 manganese must be a +7. So I'm going to just get rid of this. If it lets me, this -8, nope. Just kidding. So we won't do that. Here, we'll do this. All right. And then my Fe is +2. This Fe is +3. And this guy is +2. So my manganese is going from +7 to +2, which means it gained electrons, which is the reduction. And then my Fe went from +2 to +3, so that lost electrons. Leo, so that's my oxidation. So now we do our half reactions. My oxidation half reaction is my Fe2+ going to Fe3+. That's easy enough. And my reduction half reaction is going to be MnO4- going to Mn2+. So I do need this O4- because it has to be a part of one of these half reactions. Since it's already attached to the manganese, we are going to leave it as part of the reduction. So I balance the elements. Well, there's 1 Fe, 1 Fe. There's 1 Mn, 1 Mn, and it said don't balance the oxygens with coefficients. So the next thing, and this is the new part, if now we have oxygens, we add waters. So I have 4 oxygens here. I need 4 oxygens on this side. So I'm going to have MnO4 1 minus, Mn2 plus, and I'm going to add 4 H2Os because now on this side I have 4 oxygens. But unfortunately, now I'm not balanced with my hydrogens. Right, on this side, I now have 8 hydrogens that are not on this side of the equation. So what do we do to balance hydrogens? We're going to add H plus ions, and I need 8 of them. This is okay to do because these are all redox reactions are going to be in aqueous, so there's plenty of water around, so it's okay that we added the water. And in this case, it's an acidic solution, so there's plenty of H plus floating around. So these things, there's H plus available, there's water available for this reaction, so we are able then to just add waters and add H pluses because they are available. Okay, now we're ready to add our electrons. On this one, my charge is a +2 and a +3, so I'm going to go with Fe2 plus makes Fe3 plus 1 electron. And then on this reaction, let me let's see. So I have 8 positives and 1 negative on this side. So that would be a +7 that we're working with. I have a +2 and a 0. So we have a +2 over here. So I need 5 electrons on this side. I was using the blue. Let's try that again. 5 electrons. All right. Next step is we need the number of electrons to be the same. So I have 5 on my reduction. So I need 5 over here. So let's multiply this entire thing by 5. So I'd get 5 Fe2 plus makes 5 Fe3 plus and 5 electrons. Okay. The reason we have to do that is because the number of electrons lost in the oxidation needs to equal the number of electrons gained. So these Fe's are giving up 5 electrons for the reduction to accept 5 electrons. All right, now let's combine these guys. So I have 5 Fe2 plus 5 electrons from the reduction and 8 H pluses plus MnO4 1 minus makes 5 Fe3 plus and 5 electrons from the oxidation plus Mn2 plus and 4 H2Os. Now we're going to look for things that are the same and can be canceled on both sides. So that's 5 electrons, 5 electrons. Sometimes you do have H pluses and waters on both sides because if there was oxygen over here, we would have had to add waters and H pluses. So just be aware you can cancel or simplify the number of H pluses and oxygens. And in this case, we just have them on one on each side. So we're good there, like H plus on one side, but not the other type of deal. So now I'm just going to rewrite what's left. And there is my final balanced redox reaction. It is okay that there's H plus in my final answer because we have acidic solutions. So this would be an example of a reaction where you probably wouldn't expect, just looking at this, when you balance, to know that you need waters and H pluses. So the half reaction process, which is what we're doing here, is a good way to balance this type of reaction, not just looking at it and putting in coefficients. There's that answer one more time if you want to write it on your page. All right, here's one for you to try. So assign oxidation numbers. Figure out what's oxidized, what's reduced. Break it apart into your oxidation and your reduction half reactions. Balance the elements that aren't oxygen. Then balance the oxygen by adding waters. Then fix what you just did because you now added H pluses. So you'll add, or you just added hydrogen. So then you'll add H pluses to cancel out those. And then figure out your charges, add electrons. and then multiply to try to cancel your electrons and put it all back together. Set a timer for yourself for 3 minutes, and the answer will be up in 3, 2, 1. All right, so I got that the chromium was reduced and the chlorine was oxidized. So here's my oxidation half reaction. I put a big 2 in front of the chlorine to balance out. Here's my reduction half reaction. This is why it's important to balance the elements first. Yes, we're excited about the waters, but there are 2 chromiums here, so I need a big 2 in front. And then let's deal with the oxygen. So I have 7 oxygen, so I had 7 waters. That means I need 14 H pluses because 7 times 2 is 14 on this side. Now we can do the charges. This side is -2 because 2 and a -1, and this side is 0, so I had 2 electrons to my product side. Over here, I have a positive 14 and a -2, so my charge is 12, and on this one, my charge is, let's see, this is +6 and 0. So on this guy, we're going to add 6 electrons to my reactant side. Remember, reduction reactants. So if I have 2 electrons here and 6 here, I need to multiply this entire equation by 3. And what this really means is that the oxidation part of the reaction happens 3 times for every time one of the chromiums is reduced. So this guy has to happen 3 times over in order for the reduction to happen once in this balanced equation. All right, so then once I multiply these by 3, I get 6 Cl minuses and 3 Cl2s, 6 electrons. I have my 6 electrons, right? So sorry, this is my half reactions all split up. What I have here, 6 electrons, 14 H pluses, the Cr2O7 2-, 2 chromium ions, and then 7 waters. I see that my 6 electrons will cancel, and then here's my balanced equation with the reactants all together and then the products all together. All right, here's another one I would like you to try on your own. So set a timer on your phone for 3 minutes, and then I will put the answer up for you in 3, 2, 1. Here's my final answer. The only thing a little bit different about this one is you needed, because there were 2 electrons and 3 electrons, we had to multiply both half reactions by a coefficient. So we had to multiply the oxidation by 3 to get 6 and multiply the reduction by 2 to get 6 so that our electrons would cancel out. Everything else was very, very similar. Don't forget to balance your non-oxygen and hydrogens, because if you don't do that part, then when you go to add your electrons, your charges will be messed up, because really this is 2 Br minuses, so a -2. All right, here's another one. It is in basic conditions. Here's what I would like you to do though, because basic conditions is almost all the same. There's just a little tweak at the end. So I would like you to balance this one using the half reaction method. Get to the end, and then I will show you the small tweak we make because it is basic. So again, pause the video, and I'll put up the answer so far in 3, 2, 1. All right, double check. Hopefully you got this far. If not, I want you to go back, and I put my steps down, try to show it as clearly as possible, so find your mistake. But hopefully this is where we are leaving off. And normally we would be done if it's acidic, because there can be these H plus hanging out. But in a basic solution, H plus will not last long, because we know that H plus and OH minus reacts. So on this side, because I have 4H plus, I'm going to add 4 OH minus, because we know it's basic, they are going to react. Remember, if we have H plus and OH minus, that's going to combine to make 4, let's try to be a little neater, 4 HOH, which is the same as 4 H2Os. So OH minus and H plus are going to make water. So now if we look, I have 2 H2Os on this side, and this is 4 H2Os. So I have 2 H2Os and I have 4 H2Os. Those guys will cancel, and I'll be left with just 2 H2Os on this side, because 2 on the left, 4 on the right makes 2 on the right. So my final, and then I apologize, what we do to one side, we have to do to the other. So these OHs, we don't want to ruin all of our hard work balancing. So we're in basic solution. There's a ton of hydroxide floating around. So because I added 4 OHs to the left, or to the right, I'm going to add 4 OHs to the left. So my final balanced equation is going to be 4OH minus plus Mn2 plus Br2 makes 2Br minus 1 plus MnO2 plus 2 waters. So these became the 2 waters. Well, they became 4 waters that were simplified. So this is basic. Is it okay that there's hydroxide over here? Yes, because we have a basic solution, so there's a ton of hydroxide floating around. So all we did that was different was we added 4 OHs to both sides because we knew that the H plus would react to make water, and then we simplified the waters. Here's that same answer one more time, just a little sloppier. All right, last one. This one is a good challenge for you. This is a good example of why we balance with the half reactions. I can already tell this is going to be a headache, so using the half reaction method is helpful. So I want you to split this into its oxidation and reduction half reactions. It is basic solution, so when you're done, you will do that final tweak where you add the hydroxides to both sides and cancel out your waters. All right, hopefully you saw that carbon is oxidized and manganese is reduced. So we have Cn minus going to CnO, MnO4 minus to MnO2. Nitrogen, notice, was not impacted and oxygen wasn't impacted. That's okay, but they will be part of our balancing. So I balance my elements. I balance my water then by adding H2O. I balance the H's by adding H+. Over here, my elements were balanced, so I add 2 waters to balance the oxygens. I have 4 here. I already have 2, so I only need 2 waters. And then I added H+, so 4 H pluses. I figure out the charge, so a -1 and a +1. That means I need to add 2 electrons. A +3 and a 0, I needed to add 3. I multiply both so that my electrons are the same. And then here's those half reactions ready to be smooshed together. I do smoosh them together and I cancel out the electrons. I then simplified because if you look on this case, I had 3 waters and 4 waters. So that leaves 1 water on the product side. I had 8 H pluses and 6 H pluses, so really just 2 H pluses here. So here's my equation if we were in acidic solution. I had to simplify my waters and my H pluses because they were on both sides, but now we should be good. This H plus will not last long in a basic solution, so I'm going to add 2 OH minuses to my left, 2 OH minuses to my right. Those OH minuses become water, and they become 2 waters, but I already have a water over here, right? So here's my 2 HOHs. There's already 1, so let's simplify. This one cancels, and I'm just left with 1 water. So here is my balanced equation in basic solution that's balanced based off the elements and based off the charge. Hopefully this was a good overview. I'm sorry if it went a little long, but there's just a lot of steps, so good work.